What's up? Welcome to the Physics 2 solution. We're going to be solving a problem here. The problem states that there's a long, thin rod carrying a charge density of 32 nanocoulombs per meter and lies along the x-axis while moving in the positive x direction. So let's signify that here with capital V. With a speed of 2.1 times 10 to the 7th meters per second. First, we want to find the electric field at point P, where P is equal to 0, 18, 0 centimeters. Okay, so essentially that's just along the y-axis, 0.18 meters away from the x-axis. Okay, we know that our equation for the electric field is provided by a point charge as kq over r squared. We can then generalize that for an infinitesimal charge as dE equals k dq over r squared. And what we're going to do, because all of the x components of our electric field will cancel from each other. For instance, those from the right will break up into x and y components, where our x components will be dE sine of theta, and our y components will be dE cosine of theta. These will cancel, leaving us only with our cosine of theta components, where theta is the angle between our electric field and the perpendicular of our rod, crossing point P. We can then replace some variables such as dq to get terms that we know, like lambda, by setting dq equal to lambda dx, which is from our linear charge density equation. And we can replace cosine of theta equal to adjacent over hypotenuse, where our adjacent vector is going to be our distance from the point and our rod as r, and the hypotenuse, which is going to be some arbitrary length lowercase r. But what is that lowercase r? It's going to be changing as we go throughout the integral, thus we want to get in terms of other terms here since we're using dx now. Okay? We can see that r, if we have x as the length from the center of our rod to our point of our infinitesimal charge, we're going to have r equal to the square root of r squared plus x squared. Replacing that here with our cosine of theta, we'll have r over the square root of r squared plus x squared. Now plugging in to our original equation, we have dE is equal to k lambda dx over r squared, which is just going to be r squared plus x squared, because the square cancels with the square root, multiplied by our cosine of theta, which is going to be r over the square root of r squared plus x squared. We can then simplify this further by moving our variable in front of the integrand as such, and multiplying the two variables in the denominator so that we have r squared plus x squared to the 3/2. Now we can find the electric field caused by all the points along the length of this wire by taking the integral of both sides. The integral of dE is just e. Pulling out our constants, we have k lambda r times the integral of dx over r squared plus x squared to the 3/2. Okay, when we see a squared variable inside of a square root, we're going to think trigonometric substitutions, where we can set x equal to r tangent of theta. And the reason we use tangent is because we see the plus sign. Okay, when we extract our r, it's going to be 1 plus tangent of theta, which we can replace with secant of theta. Okay, but before that, we also need to find the replacement for dx. And we do that by taking the derivative of both sides here, which will give us r times secant squared of theta d theta. Replacing the terms, we then see that this is equal to k lambda r times the integral of r secant squared theta d theta all over r squared plus r squared tangent squared of theta to the 3/2. Okay? So drawing a little line here so we don't mix up our math. We're going to see that E is equal to, and simplifying by pulling out the r squared and then setting 1 plus tangent squared theta equal to secant squared theta, we'll have E equal to k lambda r squared from pulling that out times the integral of secant squared theta d theta all over r times, so r cubed secant cubed theta. Okay? And then we can further simplify this. R divided by r cubed is just going to be 1 over r, I'm sorry, this should be a squared, right? We have 2 r's over here. So r squared over r cubed should thus be 1 over r. So we have E is equal to k lambda over r times the integral of cosine of theta d theta. But what is our bounds for this integral? Okay, if we look back, if we integrate from the center going outwards, we'll have theta equals 0 to theta equals 90 as we go along the right long rod. Thus we'll have 0 to 90 as our bounds. And then solving this, we have 2k lambda over r times the integral, times the integral of cosine of theta, which is evaluated as sine of theta from 0 to 90, which is just going to be 2k lambda over r times 1 minus 0. Okay, now plugging in our values, we have 2 times k, which is just going to be 9 times 10 to the 9th, times our lambda, which is going to be 32 times 10 to the negative 9 for our nanocoulombs, coulombs per meter, all over our r, which is going to be 0.18 meters, which further evaluates to 3,198.71 volts per meter. And our direction is going to be in the positive x direction. But yes, that is all.